Just for fun number 2. This is another one of our just for fun little lab projects. We had you open up a earlier project, bit shift final, and then save it as just for fun number 2. We had you modify the logic, and the goal of the challenge, we have cartons of varying lengths arriving by gravity conveyor and being pulled onto a belt conveyor. We have no barcode reader, but if we know the length of the carton, we can identify its contents. If we can monitor the length of the conveyor travel with the photo eye 2PE at the entrance of the conveyor, we can determine the length of the carton. If we know the speed of the conveyor and we know that the photo eye is blocked, then we can determine the length. So in our logic, we attached local one-eye data bit 1 as the source bit for the BSR instruction. So we're using local one-eye data 1 as our photo eye 2PE. Also, we have a device that we use to determine length. Actually, it's a pulse generator that has wheels of a known circumference that ride on the conveyor belt. And when you order these pulse generators, you order them by specific circumference of the wheels, and then the pulse generating electronics are ordered by specific pulses per revolution. In order to simplify our application, we're skipping any of the calculations, and we're just stating that this device connected to one of our inputs generates one rising edge pulse per 1 inch of travel of the surface of the conveyor belt. If it puts out 6 pulses, then the conveyor belt traveled 6 inches. We had you edit the logic that you renamed, create some new tags, program scoped. There are many ways we could do this. If we were actually in a real application wanting to get measurement or detection of length, we probably wouldn't do it this way. We did it this way because we wanted to demonstrate the mask equal. So we like to pull in the instructions we've been working with in our just for fun projects. And I realized that the edit did not leave much of the original shift program, but it did allow you to start from a more familiar territory. Rung 0 allows you to view an object moving on the conveyor, each group of on states that are separated on both ends by off states. That represents a carton. 2 successive on states bounded by an off state on both ends is a 2-inch carton. 3 on states bounded by off states on both ends, 3 inch, and so on. Okay, rung number 1 represents your pulse generator. So rung number 1, and you would not have any pulses generated unless the conveyor is on. So we're using the conveyor on switch, and we don't have a conveyor motor in our logic. We're just saying when you flip on input 0, the conveyor's on and moving. And then we have a multiplication or multiply instruction. And by the way, this instruction does manipulate the value of pulse frequency preset. The destination is the preset for the pulse frequency timer data type. Other than it affecting the destination or the preset for the pulse freq timer data type, it has no other effect or effect anywhere in the logic. It's just there to make sure that the preset gets set properly anytime you run this. So looking at that rung, conveyor switch is on, so rung out true. The multiply instruction has no effect whatsoever on the rung state. It's just an execution. So the next instruction that actually affects the true-false state of the rung is the pulse frequency done bit. And the pulse frequency timer data type is controlled by the next instruction, which is a timer on delay set with a preset of 1000. And that preset of 1000 was determined by that multiply instruction, which means that if the pulse freq timer is not done, then it enables this timer data type and it counts up to 1,000 thousandths of a second. As long as it is counting, it enables this on-delay timer that has a preset of 100. So when this starts timing, it enables this timer. This timer goes on basically for 100 milliseconds, which would be a tenth of a second. So scan by scan, this timer continues to accumulate until it hits 1,000. This is now false. The rung goes false, and both of these timers are reset, and then it starts over again. The end result is, as long as the conveyor is on, every second, every 1,000 milliseconds, this timer is on for 100 milliseconds. The timer timing pulse is right here. Now, you're not going to see this go on for a tenth of a second. It's unlikely, but we know that it is because this keeps resetting. So we know that this bit is not true indefinitely. Otherwise, you would not see the accumulate getting near 1,000 and then going back towards 0. So we know that the timer timing pulse here is going on, but we're not enabling tracking. If I enable tracking by toggling on that bit, we still can't see anything. To prove that this is shifting though, in other words, every 1 second this comes on and it shifts, we'll throw in a bit here. So I'll toggle this one on, and you'll see that every 1 second it shifts. That's proof positive that this instruction is being executed. And of course, that's going to shift all the way down to any array element 1, bit 0, and then off into bit space. You've seen that often enough. Okay, so rung 1 is a pulse generator. It takes the place of the conveyor moving and generating pulses. That's all it does. The pulse that we simulated with rung 1 is used in rung 2. So every 1 second, the BSR is executed. So whatever data, whatever bit pattern, whatever bit states are in any array 1 are shifted to the right, meaning from more significant to least significant, from bit 31 towards bit 0, once a second. Now this pulse, I made it 100 milliseconds just because that's a nice looking pulse. You could make that maybe 1 millisecond get away with it. I wouldn't go any less than 10. And sometimes we call that a pulse stretcher, where we have a change of state, but we want that state to stay changed for a specific length of time. We would use a TON like this. Okay, going to rung 3. We have enabled the 2-inch detection circuit. So skip the mask equal just for a second. The next instruction is an output 0, that is going to come on if a 2-inch carton is detected. And then the count up instruction is going to increment by 1 for each false to true transition that's wrong. So we go back to the mask equal, and we are comparing the 32-bit pattern of any array 1, which you can see part of it up here. We're going through a mask with this value. Now that value doesn't mean anything to you. It doesn't mean anything to me. Right at this moment, I happen to know exactly what the bit pattern is, only because I'm working on this right this minute. But if tomorrow, if you ask me what's the 32-bit pattern for this humongous value, I wouldn't have a clue. So we're comparing the bit pattern in any array 1, those 32 bits, with these 32 bits, and the name of that tag is 2-inch. So this is the pattern that we're looking for to declare that there is a 2-inch carton detected. To emphasize this, we're going to go to Window, well, don't have it open. We'll open up Program Tags, and we'll go to 2-inch. We'll go to 2-inch pattern, and we'll change that to binary so we can see the bit pattern that we need to see to declare that there's a 2-inch carton. More important than this is the mask. We go to the mask. Remember, we're comparing this. This is the mask that we're passing any array 1 through to do our comparison. This would be bit 31, 30, 29, 28, 27, 26, 25, and so on, down to bit 0. So what we're declaring here is that we want to compare these 6 bits with our any array 1 bit pattern to see if there's a match. But these 6 bits right here, this means that this 6-bit window is the window that we're looking through. So this mask only determines what bits we can see to compare with. Now for the 2-inch pattern, we're looking for these 2 bits. Go down here to 2-inch. We're looking for these 2 bits to be on and the other 4 bits to be off. So if you drop straight down from these 6 bits, which are enabling the compare, straight down you'll see 0, 1, 1, 0, 0, 0, which means to say that we see a 2-inch carton, we have to see at these 6 locations exactly 0, 1, 1, 0, 0, 0. If we're doing a 3-inch, then we need to see this pattern, 0, 1, 1, 1, 0, 0. And if we're looking for a 4-inch, we need to see 0, 0, 1, 1, 1, 1, 0, 0. But of the 6 bits, we need to, of the 6 bits that we're looking at here through the mask, we need to see 0, 1, 1, 1, 1, 0. Because the mask only has these 6 bits on, it's only enabling the equal instruction to compare these 6 bits with these 6 bits. These 6 bits, this is the source. This would be source A up here. This is the bit pattern of bit shifting on the conveyor. And we are specifically looking at bit 30, 29, 28, 27, 26, and 25. 27. We're looking at bit 30, 29, 28, 27, 26, and 25. So our mask right here, these 6 on states, are comparing these 6 states with either a 2-inch pattern, a 3-inch pattern, or a 4-inch pattern to determine if we have detected a carton. And that's what these 3 rungs right here do. So we could enable them all. We won't. We'll leave just that one enabled. And we do have our system all on, so it is shifting, even though you can't see it shift. It's shifting. We're generating a pulse once a second. Now remember that the photo eye, 2PE, is local 1I data 1. So I'm going to hold local 1I data 1 down for just 1 pulse. So whatever blocked that photo eye only blocked it for 1 second, but less than 2 seconds. There were no cartons detected. If I hold it down for 3, you see that because the 2-inch is enabled, we don't see anything come on here and we don't see anything accumulated. Even though we did pass a 3-inch through, we did not enable the 3-inch logic here. We've only enabled the 2-inch detection. So now I'm going to hold it down for 2 pulses. I just saw the light come on and the accumulate. We'll do that one more time so you can watch this output and this accumulate. Two-inch detected and it increments. Now let's do we'll toggle this on and we'll do a 2-inch again. So watch the 2-inch detected. Oh, I did a 3 accidentally. Held it down too long. So you see that this incremented 1 here. Let's do the 2 again. You see the 2-inch detected and incremented by 1, the 3-inch did not, even though it's enabled. So we'll enable all 3 of them. So I'll hold down, we'll do a 4-inch carton. 1, 2, 3, 4. You see the 4-inch is detected and it increments by 1. We'll do a 2. 2-inch detected. We'll do a 3. 3-inch detected. The end result of this real simple logic is that we detected on a virtual conveyor. If this was a real conveyor, this would still work. We'd have a real photo eye. We'd actually have a conveyor belt moving. We'd have a pulse generator, which is a physical device, not rung 1, that's simulating the pulse generation. So that was really the entire essence of the Just for Fun. There was a question, did you see any on-state shifting across the range of bits? This one was when we did a simple 1 bit. And the answer should be yes. You should have seen one going across there. And then there was another question at the end of the Just for Fun. Why do we need a leading and trailing off state? Well, we need leading and trailing edges of the carton detected. That would be singulation of the virtual objects. The pulse just went on and stayed on. 3, 4, 5, 6. If that was a couple cartons resting up against each other, in other words, there was no space between them, it would have been seen as one long carton and not separate cartons. The cartons have to be singulated, and of course they would be in our conveyor application because the cartons come down and hit the leading edge of the conveyor on a gravity conveyor. It's not driven. It's just gravity rolls it down. It hits the edge, and we have the conveyor designed so it pulls the carton onto the conveyor fairly quick. So any subsequent cartons backed up on the gravity conveyor would be slow to continually roll down and hit the leading edge of the conveyor. So they would singulate. They would naturally create spaces in between them. Then the last questions, I showed you a bit pattern, and we will disable this, and we'll go to, I turned it off, program tags, and we're going to go to any array, element 1, and we're going to switch that to binary. And I had a pattern on there of so you can punch these in yourself. The question was, how many cartons are on this conveyor? Well, take your groups of on states, and to be a group that has to be 2 or more. There's one separated by off states. There's another, there's another, there's another, there's another, there's another. So that's 5. 1, 2, 3, 4, 5 cartons. How many of each size? That's a 2-inch, that's a 3, that's a 4, that's a 4, that's a 2. So there's 2 at 2 inches, 1 at 3 inches, and then these 2 right here are 4-inch. So we have 2 at 4 inches.